Imagine the first human who looked up after nightfall and felt that strange electric shiver that still runs down your spine when you see a sky unspoiled by city lights, a sky so dense with stars they look like frost on black glass. And imagine that person realizing, perhaps without words, that those points of fire were not merely decoration, but something vast and ordered and impossibly distant, and that their own small life was being measured, silently and precisely, by those cold, shining watchers overhead. Tens of thousands of years before anyone carved equations into paper or traced star paths on vellum, people were already folding the heavens into their lives. In caves like Lascaux, where animals run across the walls and some specks of paint, arranged in curious patterns, seem less like random dots and more like a memory of the Pleiades and Orion, immortalized beside bison and horses as if the stars were simply part of the same great herd roaming across the night. When hunter-gatherers followed the seasons, they did so not with calendars on their walls, but with constellations in their minds, knowing that when a certain star rose just before dawn, the rivers would soon flood, the herds would move, or the berries would ripen, and some of the earliest amazing astronomy facts were not about galaxies and black holes, but about which small patch of the sky meant survival for the year to come. Long before the word astronomy existed, the sky was already a textbook with no author and no end. In ancient Mesopotamia, by the slow brown rivers of the Tigris and Euphrates, scribes in temples watched the heavens not for beauty but for omens, scratching clay tablets with wedge-shaped marks that, astonishingly, we can still read today, listing eclipses, planetary motions, and the first known systematic star catalogues, where stars were grouped into constellations and each given a name, as if the act of naming them might tame the terrifying idea that the motions of those distant fires could somehow foretell the fate of kings and empires. Those Babylonian astronomer priests built their knowledge over centuries, night by night, tablet by tablet, until they knew with unnerving accuracy when the moon would vanish into Earth's shadow, an event so frightening that in many kingdoms drums would beat and people would shout and clash weapons to scare away the dragon or demon believed to be devouring it. While in the temple courtyards, the astronomers quietly checked off one more successful prediction and added another brick to humanity's understanding of celestial cycles. From Babylon spread the notion that the sky was not merely a canvas of myths, but a clock and a ledger. And by the time this knowledge travelled westward, carried by traders and conquerors, the Greeks inherited more than loose stories. They inherited tables of planetary positions and eclipse records, and with them the courage to ask questions that pushed beyond omens toward the radical possibility that the sky followed rules that the human mind could grasp, even if those rules belonged to a realm so distant that no one could ever touch it. In Miletus by the Aegean, Thales is said to have predicted an eclipse that halted a battle, turning day to sudden night, causing the warring armies of the Medes and Lydians to drop their weapons in terror, and whether he truly foresaw it or borrowed Babylonian records, that single story became a symbol of something profound. The idea that a human, standing on a small patch of dirt, could look up, read the sky's patterns, and know in advance exactly when the sun itself would disappear. Pythagoras and his followers, intoxicated with numbers, took the next audacious step, whispering that the heavens must be ruled by pure mathematical harmony, that the intervals of music and the distances between planets were somehow siblings, so that when you listened to a lyre you were, in a sense, eavesdropping on the secret geometry of the cosmos, and though their music of the spheres remained metaphor, it contained the seed of a deeper truth, that astronomy might one day become not a collection of omens, but a science of exact relationships. When you hear that a star is so far away its light left before humans built the pyramids, you're hearing an echo of a question wrestled with in ancient Greece, where Anaxagoras dared to claim that the sun was not a god's chariot, but a fiery stone larger than the Peloponnese, and the moon a cold, earthy body with mountains and valleys, illuminated only by reflected sunlight, a claim so bold that it cost him exile, yet laid the conceptual groundwork for treating celestial objects as physical things, governed by the same laws as earthly rocks and rivers. Then, in the 3rd century BCE, somewhere in the learned corridors of Alexandria, Aristarchus of Samos performed a conceptual miracle so far ahead of its time that it would take almost 1800 years for the world to catch up. By using simple geometry and the phases of the moon, he estimated the relative sizes and distances of the sun and moon, and concluded that the Sun must be vastly larger than Earth, and following this colossal clue, proposed that Earth and the other planets must orbit the Sun, rather than everything circling the Earth as common sense and tradition insisted. Imagine holding that thought in a world where everything around you, from falling stones to the motions of the stars, seems to testify that the Earth is solid, central, and unmoving, and then daring to say aloud that the ground beneath your feet is in fact whirling around an invisible centre, dragging the moon, the seas, and the air along with it. Aristarchus saw it, wrote it, and was mostly ignored, but his heliocentric shockwave never completely died, sleeping in dog-eared manuscripts until other minds, centuries later, would awaken it. Closer to his time, another Greek, Eratosthenes, peered into a well at Siena where, on the summer solstice, the noon sun shone straight down and cast no shadow, then measured the shadow of a pole in Alexandria at the same moment, and from the modest angle of that sliver of shadow, calculated the circumference of the entire Earth with an error of only a few %, proving with a stick and a keen mind that astronomy could turn a local observation into a measurement of the planet's full roundness and size. The sky was not only a laboratory but a map, and across the Mediterranean sailors steered their ships by familiar star patterns, while further east, in the vastness of the Pacific, Polynesian navigators memorized hundreds of stars in carefully organized star paths, using the rising and setting points of each to cross open ocean with a precision that astonished European explorers who stumbled upon their islands centuries later, unaware that a sophisticated, orally transmitted celestial navigation system had been guiding voyages between specks of green in a blue immensity long before compasses or sextants visited those waters. Farther east still, in ancient China, imperial astronomers were already keeping the oldest continuous record of the sky we possess, labouring under the weight of responsibility because a poorly interpreted comet or an unexpected guest star might be read as a bad omen for the emperor, and in 1054 they faithfully recorded a brilliant new star that appeared near the horns of Taurus during daylight, and slowly faded over months, unaware that they were witnessing the birth of what we now call the Crab Nebula, the remnants of a supernova whose expanding filaments still glow and whose pulsar core still drums out radio pulses more than 9 centuries after their brushes wrote its first entry into human history. Supernovae had flared before and would flare again, but their records, preserved in Chinese, Japanese, and Islamic chronicles, became crucial to later astronomers trying to understand stellar evolution, reminding us that every note a patient scribe jotted down by lamplight could, 1,000 years later, become a clue in an entirely different cosmic puzzle, and that astronomy, more than almost any other science, depends on a chain of witnesses stretching across cultures and centuries. From Greece emerged not only bold conjectures but also something every modern stargazer silently relies on: the first truly systematic star catalogues, like that of Hipparchus in the 2nd century BCE, who compared earlier observations with his own and discovered that the positions of certain stars had slowly shifted relative to the equinoxes, a phenomenon we now call the precession of Earth's axis, caused by the slow wobble of our planet as it spins, so that over a cycle of about 26,000 years the North Pole traces a wide circle in the sky, turning different stars into the pole star over long epochs. When Hipparchus realized this, the very idea that the celestial sphere itself could drift must have been disorienting, because it revealed that even the apparently fixed background of stars was not a perfect eternal grid, but part of a much less rigid machine, one where almost everything was slowly in motion, and his measurement of precession stands as an early demonstration that nothing in the cosmos, not even the framework against which we measure motion, remains absolutely still. The Greeks imagined crystalline spheres carrying planets like jewels, rotating with sublime steadiness, but as observational data piled up, especially concerning the erratic loops of planets like Mars, their geometric models grew intricate and baroque, culminating in the colossal mathematical edifice of Claudius Ptolemy in the 2nd century CE, who, working in Alexandria, constructed a geocentric system using deferents and epicycles that could reproduce planetary motions with remarkable accuracy, a model so persuasive and conceptually satisfying that it reigned almost unchallenged for over 1,000 years, binding together Greek geometry, Aristotelian physics, and a philosophical conviction that Earth must sit at the centre of creation. Meanwhile, in the Islamic world, as political power and cultural energy shifted east and south, with the rise of new caliphates, the torch of astronomical inquiry passed to scholars in cities like Baghdad, Damascus, Ray, Isfahan and Cordoba. Where the night of power in Ramadan was calculated with care, prayer times and Qibla directions demanded precise understanding of the sky, and the works of Aristotle, Ptolemy and others poured into Arabic through massive translation projects, to be not only copied, but challenged, corrected and extended. In the early 9th century, under Caliph al-Ma'mun, the House of Wisdom in Baghdad sponsored detailed observational programs, including one in which astronomers measured the length of a degree of latitude along Earth's surface, by sending surveyors to pace out a north-south baseline in the desert, using stars to ensure their direction was true. And from their results they derived a circumference of Earth impressively close to the modern value, echoing and refining the ancient Greek measurements and demonstrating once more that astronomy could be married to geography and state-sponsored science. At observatories like Maraga in Persia, and later Samarkand under Ulugh Beg, huge instruments rose from the ground, giant quadrants and sextants carved into stone, armillary spheres taller than a person, because before telescopes, the only way to increase accuracy was to build larger devices to read angles more finely. And with these colossal tools, Islamic astronomers compiled star catalogues more precise than any before them, noted irregularities in Ptolemy's parameters, and proposed subtle geometric innovations that, centuries later, would quietly infiltrate the work of Copernicus via Latin translations. Al-Battani refined the length of the tropical year, and the obliquity of the ecliptic. Al-Biruni wrote with ease about Earth's rotation as a plausible possibility, and Al-Sufi produced the Book of Fixed Stars, which not only described constellations but mentioned in the year 964 a faint little cloud in the constellation Andromeda, the earliest known written observation of the Andromeda galaxy by a human eye, a smudge of light that we now know is a vast spiral of hundreds of billions of stars bearing down on the Milky Way in a slow-motion galactic collision that will begin in earnest about 4 billion years from now. In those same centuries, as Europe wrestled with political fragmentation and the slow rebuilding from the Western Roman Empire's collapse, astronomy lived in quieter corners, in monasteries where monks tracked Easter's shifting date by studying the lunar cycle, in cathedral schools where the 7 liberal arts included the mathematical quadrivium crowned by astronomy, and in the imaginations of poets like Dante, who, when he guided his characters up through the spheres of Ptolemaic heaven in the Divine Comedy, laid out a mental planetarium that mirrored the scholastic cosmos of his age, with Earth at the centre wrapped in nested shells of moon, planets, fixed stars, and the crystalline primum mobile. Yet even in this geocentric universe, cracks appeared, often prompted by practical needs. Sailors on longer ocean voyages required better ways to find their latitude and, more challengingly, their longitude, and their reliance on Polaris and other navigational stars forced more careful charting of the heavens. Slight discrepancies between predicted and observed positions accumulated, like dust in the corners of a room, waiting for someone obsessive enough to sweep them into the light. That someone was not one person but a chain, and the first link we often name is Nicholas Copernicus, a canon from Turin who, living in the late 15th and early 16th centuries, absorbed Greek and Islamic astronomy through Latin texts, studied in Italian universities, and returned to a life that, at first glance, looked more administrative than revolutionary. Yet in the quiet months of his duties, he worried over Ptolemy's epicycles, searching for a simpler, more coherent arrangement that would preserve circular motions yet avoid inelegant mathematical distortions. Copernicus's solution, whispered in manuscript long before it thundered into print, was to take Aristarchus's old heliocentric idea off the shelf, dust it, and rebuild the entire planetary system around the Sun, not as a mere speculation, but as a full geometric model that could calculate positions. When De Revolutionibus Orbium Coelestium finally appeared in 1543, the year of his death, its preface cautiously framed heliocentrism as a computational convenience. Yet in its pages the Earth spun daily on its axis and raced annually around the Sun, dethroning it from the cosmic centre and turning it into a planet like the others. The shift was not instant. Most readers treated Copernicus as an intriguing alternative within the existing mathematical tradition, but a few, such as the fiery Italian Dominican friar Giordano Bruno, leaped far beyond his cautious lines, proclaiming that an infinite God must have created an infinite universe full of countless suns and worlds, some perhaps inhabited, making the Copernican cosmos not just a rearranged set of spheres, but an open ocean without walls, a claim that combined mystical daring with logical extrapolation and contributed, along with theological heresies, to his trial and execution in 1600. Even as philosophy grappled with these implications, a Danish nobleman named Tycho Brahe was building on his private island of Hven what was essentially the last great pre-telescopic observatory, outfitted with massive, meticulously crafted instruments that allowed him to chart planetary and stellar positions with unprecedented precision, and in 1572 his eyes caught a startling sight near Cassiopeia, a new star where none had been recorded, bright enough to rival Venus, which slowly faded over months, and by noting its lack of measurable parallax against the background stars, he proved that it lay in the supposedly unchanging realm of the fixed stars, shattering the Aristotelian doctrine that the heavens above the moon were perfect and immutable. That new star was another supernova now catalogued as SN 1572, and Tycho's study of it, along with his investigations of a major comet in 1570, which he showed moved through the planetary spheres without resistance, dismantled the crystalline sphere conception and suggested instead a more fluid celestial medium, one in which bodies could roam on paths not bound to perfect circles of transparent glass. His mountains of observational data would become the raw material for one of the most important theoretical leaps in astronomy's history. Johannes Kepler, a German mathematician with a mystical bent, who believed God had arranged the cosmos according to geometric solids, inherited Tycho's records after the Dane's death and set about the grueling labour of fitting Mars's motion to hypothesized orbits. The more he tried to force the data into circles, the more stubbornly small discrepancies remained, until, unable to ignore them, he took the bold step of abandoning the age-old dogma of circular perfection and allowing planets to move on ellipses with the Sun at one focus. From that act of intellectual capitulation to the evidence emerged Kepler's three laws of planetary motion. Planets travel in ellipse with the Sun at one focus. They sweep out equal areas in equal times, moving faster near perihelion and slower near aphelion. And the square of a planet's orbital period is proportional to the cube of its average distance from the Sun, a simple mathematical harmony that, centuries later, would echo in the orbits of distant exoplanets, as astronomers applied the same relationship to systems light years away, showing that the patterns Tycho recorded in the cold Danish nights apply equally in alien skies. While Kepler decoded orbital geometry, an Italian professor of mathematics named Galileo Galilei turned a new technological toy, the spyglass recently invented in the Netherlands, toward the heavens, grinding his own lenses, improving magnification, and in 1609 aiming the telescope skyward for the first time in human history, immediately stumbling into a cascade of discoveries that forever altered our view of the universe. Through Galileo's crude but revolutionary optics, the moon ceased to be a smooth, polished sphere, and revealed itself as a rugged landscape of craters, mountains and shadows, illuminated obliquely by the sun just as earthly hillsides are. While the Milky Way, long seen by naked eyes as a milky streak, dissolved into countless individual stars too faint to distinguish unaided, betraying its true nature as a dense river of suns wrapped around our own in a vast, flattened disk. He turned his telescope toward Jupiter and saw, to his astonishment, 4 small stars that changed position night after night yet always stayed close to the planet, tracing out patterns that could only mean one thing. They were orbiting Jupiter itself, moving around another world in a miniature solar system, and their existence dealt a blow to the notion that everything must circle Earth, while also suggesting that celestial centres of motion could be multiple, a powerful visual metaphor for Copernicus's claim that our world was not uniquely privileged. Saturn, seen through Galileo's modest instrument, presented a bizarre and incomprehensible shape, ears, or handles, as he described them, because his optics could not resolve the planet's rings cleanly. Yet even this enigmatic sight hinted that the planets were not simple wanderers, but hosts to bewilderingly diverse structures, and when he focused on the Sun, dark spots marred its disk, slowly drifting across, changing shape, even appearing and disappearing, providing irrefutable evidence that the great source of light and warmth was not perfect and spotless, but turbulent and restless, with churning magnetic storms staining its face. Galileo's public advocacy of heliocentrism, fueled by these telescopic revelations, eventually brought him under the scrutiny of the Roman Inquisition, and after a complex philosophical and political struggle, he was tried, forced to recant aspects of his teachings, and confined to house arrest. Yet even in his enforced solitude, he continued to write, and his work on motion and inertia would feed directly into the mind of another Englishman, who would finally weld together the motions of falling apples and orbiting moons into a single, dazzling framework. Isaac Newton, born in 1642, the year of Galileo's death, grew up in a turbulent England of civil wars and plagues, yet in the quiet of his own Annus Mirabilis in 1665-1666, while the plague closed Cambridge and he retreated to his family home in Woolsthorpe, he developed both the calculus and, more importantly for our story, the law of universal gravitation, realizing that the same force that pulls an apple toward Earth also governs the curve of the moon's path around our planet, and, by extension, the motions of all celestial bodies. Newton's inverse square law of gravitation, combined with his three laws of motion, provided an exquisite explanation for Kepler's empirical rules, showing that elliptical orbits, equal areas in equal times, and the harmony between orbital period and distance all emerge naturally when you let masses attract each other with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Suddenly, the heavens were no longer a separate realm of perfection, but a grand stage on which the same formulas that describe a rolling cart also dictate the dance of planets around the sun. With Newton, astronomy became predictive at a new level. If you knew the masses and positions of planets at one time, you could, in principle, calculate their positions far into the future or reconstruct their past. And this theoretical power soon found a spectacular showcase in the work of Edmund Halley, who noticed that bright comets recorded in 1531, 1607 and 1682 had very similar orbital elements, and correctly predicted that they were the same comet returning roughly every 76 years, an icy visitor whose next appearance he forecast for 1758, long after his own death. When Halley's comet did indeed blaze across the night sky that year, precisely on schedule, its punctual arrival was a triumphant confirmation of Newtonian gravity operating on a body swinging from the outer darkness into the inner solar system and back again, proving that comets were not random omens but loyal members of the Sun's extended family, following elongated ellipses that carried them past the orbits of giant planets and out toward the Kuiper belt before gravity turned them inward once more. The 18th century saw telescopes grow larger and more sophisticated, as artisans learned to grind bigger mirrors and lenses, and among the most tireless users of these instruments were William Herschel and his sister Caroline, German-born musicians turned British astronomers who, in painstaking surveys of the night sky, catalogued thousands of nebulous objects, and in 1781 discovered a new planet, Uranus, almost by accident, when William noticed what he thought was a comet but which, on further observation, revealed itself as a distant, slow-moving world doubling the radius of the known solar system at a stroke. This expansion of the solar neighbourhood set off a chain of questions. If a new planet had lurked unseen between Saturn and the stars until a careful observer noticed its deceptive, star-like appearance, how many more might wait beyond, and what shapes and sizes would they take? And did the faint hazy patches the Herschels recorded represent unresolved clusters of stars, regions of glowing gas, or entire island universes like the Milky Way itself? Their careful sketches and notes became the seeds for both galactic astronomy and the search for structure on ever larger scales. Astronomy also began to turn inward, to the properties of light itself, when in the early 19th century Joseph von Fraunhofer built precise spectroscopes and found that the sun's otherwise continuous spectrum, when spread into a rainbow, contained hundreds of dark, narrow lines at specific wavelengths, a barcode of missing colours that, though he did not know it, encoded the fingerprints of elements in the solar atmosphere absorbing particular frequencies, and when Gustav Kirchhoff and Robert Bunsen later deciphered this code, matching laboratory emission lines to Fraunhofer's dark gaps, astrophysics was born, the union of astronomical observation with physical theory. With spectroscopy, a new kind of amazing fact became possible. You could look at a star so far away that it appeared as nothing more than a point of light to even the biggest telescope, and from the pattern of lines in its spectrum determine its chemical composition, temperature, velocity, and even the pressure at its surface, turning that single gleam into a rich dossier of physical properties and revealing, with some philosophical shock, that the stars were made chiefly of hydrogen and helium, with a smattering of heavier elements, not of alchemical quintessence or heavenly crystal. Mid-19th century astronomers also waged a decades-long campaign to answer a question that had haunted observers since antiquity. Could they detect the parallax of stars, the tiny yearly shift in a star's apparent position relative to more distant background objects as Earth swings from one side of its orbit to the other, a shift so minuscule that it had eluded all previous efforts and which skeptics of heliocentrism had claimed as evidence that Earth might indeed be stationary? In 1838, Friedrich Bessel finally measured the parallax of the star 61 Cygni, finding it to be about a third of an arc-second, a wobble so small that you would need 10,000 such angles to span the width of the full moon. From that tiny displacement he calculated a distance of about 10.4 light-years for 61 Cygni, marking the first time humans had directly measured how far away a fixed star lay using purely geometric means. And suddenly the stellar universe, which had seemed like a painted dome, acquired depth, with some stars revealed to be closer, and others vastly farther. And the concept of a light year, the distance light travels in 1 year, about 9.46 trillion kilometres, emerged as the only unit large enough to express these gulfs without drowning in zeros. In the late 19th and early 20th centuries, observatories like Mount Wilson in California and Lick in the Coast Range pushed telescope sizes into the 60 and then the 100-inch class, placing enormous glass mirrors atop sturdy mountings at high altitudes where the air was steadier, and astronomers such as George Ellery Hale, a master organizer and institutional builder, orchestrated the creation of ever more powerful instruments, convinced that bigger mirrors meant fainter objects, and fainter objects meant deeper views into space and time. It was around this period that women computers at Harvard College Observatory, including Williamina Fleming, Annie Jump Cannon, Antonia Maury, and Henrietta Swan Leavitt, performed meticulous classification of stellar spectra and brightnesses, work that the male directors often considered tedious, yet which yielded some of the most profound discoveries in astrophysics. Among them Leavitt's realization that certain pulsating stars in the Magellanic Clouds, called Cepheid variables, exhibited a tight relationship between their pulsation period and intrinsic luminosity. The longer the period, the brighter the star. Leavitt's period-luminosity relation turned Cepheids into cosmic yardsticks. By observing how often a Cepheid brightened and dimmed, you could infer its true brightness, compare that to how bright it appeared, and from that ratio compute its distance, extending the cosmic distance scale far beyond the reach of parallax. And when, a decade later, a young astronomer named Edwin Hubble began hunting for Cepheids in spiral nebulae with the 100-inch Hooker telescope on Mount Wilson, he would use her law to answer one of the most contentious questions of his time. Were those spiral small gas clouds inside our Milky Way or island universes of stars far beyond it? At the start of the 20th century, many astronomers still believed that the Milky Way comprised the entire universe, and that the faint spiral smudges catalogued by Herschel and others were minor condensations within it. In 1920, during the famous Great Debate between Harlow Shapley and Heber Curtis, they clashed over the scale of the cosmos, with Shapley arguing for a large Milky Way with the Sun far from its centre and the spirals nearby, and Curtis contending that the spirals were external galaxies. Neither had decisive evidence, but both would be overtaken by Hubble's patient, photographic assault on the problem. Using long exposures on glass plates at Mount Wilson, Hubble identified Cepheid variables in the Andromeda Nebula and the Triangulum Nebula, measured their periods, inferred their distances using Leavitt's relation, and found values on the order of 1 million light-years or more, vastly beyond even the largest proposed size for the Milky Way, thereby demonstrating that Andromeda and Triangulum were not clouds within our galaxy, but separate galaxies altogether, each containing billions of stars, turning our Milky Way into just one island among countless others in a cosmic archipelago with no obvious shore. But Hubble did not stop there. Working with Milton Humason, he gathered spectra of more distant galaxies and noticed that their spectral lines were systematically shifted toward the red end of the spectrum, indicative of motion away from us. And when he plotted this recessional velocity against distance, he found a roughly linear relationship, now called Hubble's law, showing that the farther a galaxy lies, the faster it recedes, an empirical discovery that dovetailed with solutions of Einstein's general theory of relativity and led to the startling picture of an expanding universe in which space itself stretches and carries galaxies apart like raisins embedded in rising dough. General Relativity, published by Albert Einstein in 1915, reimagined gravity not as a force acting at a distance, but as the curvature of space-time caused by mass and energy. And its equations admitted dynamic solutions, universes that expand, contract, or oscillate, though Einstein himself initially favoured a static cosmos and introduced a cosmological constant into his equations to hold it up against gravitational collapse, a term he later called his greatest blunder, after Hubble's observations made an expanding universe impossible to ignore, even as later generations of cosmologists resurrected the cosmological constant in a new guise to explain dark energy. The idea that the universe had once been denser, hotter, and smaller in the past implied that, if you ran the cosmic expansion backward far enough, you would arrive at an initial state of extreme concentration, an early fireball later dubbed the Big Bang, and theorists predicted that such a hot infant universe should have left behind a faint afterglow of microwave radiation, cooled by expansion to just a few degrees above absolute zero, filling all of space. In 1965, Arno Penzias and Robert Wilson, working with a horn antenna in New Jersey, stumbled upon a persistent isotropic radio noise they could not eliminate, even after chasing off pigeons nesting in their instrument, and soon realized, with help from cosmologists at Princeton, that they had unwittingly detected the cosmic microwave background. That afterglow, a nearly perfect blackbody spectrum at about 2.7 Kelvin, turned out to be an extraordinarily rich source of cosmic information, its tiny temperature fluctuations mapping the seeds of future galaxies laid down when the universe was just 380,000 years old, and satellites like COBE, Diasmap, and Planck have since charted its angular power spectrum with exquisite precision, allowing cosmologists to infer the universe's age, 13.8 billion years, its geometry, remarkably flat on large scales, and its composition, dominated not by the ordinary matter of stars and gas, but by dark matter and dark energy. Dark matter entered the scene slowly, first as an oddity in the 1930s when Fritz Zwicky measured the velocities of galaxies in the Coma cluster and found them too high for the cluster to be bound by visible matter alone. Then again in the 1970s when Vera Rubin and Kent Ford studied rotation curves of spiral galaxies and discovered that stars in the outer regions orbited just as fast as those near the centre, defying the expected Keplerian decline and implying that some invisible mass halo surrounded each galaxy, outweighing its luminous components by a factor of 5 or more. Despite decades of effort, dark matter has not yet been directly observed in the laboratory. Its presence is inferred from gravitational effects on galaxies, clusters, and the tapestry of the cosmic microwave background, and leading candidates include weakly interacting massive particles, axions, and perhaps primordial black holes, though none has yet claimed victory, reminding us that astronomy sometimes points to the existence of entire categories of substance that evade our detectors even as they sculpt the large-scale structure of the universe. Dark energy, even more enigmatic, came to light in the late 1990s when two independent teams of astronomers, studying distant Type Ia supernovae as standard candles, found that the universe's expansion was not slowing down under gravity's pull, as everyone had expected, but actually accelerating, as if some repulsive component of the cosmos were pushing galaxies apart ever more quickly. In modern cosmological models, this dark energy accounts for about 68% of the total energy density of the universe, with dark matter adding 27% and ordinary baryonic matter a mere 5%, leaving us in the humbling situation of understanding only a small fraction of what reality is made of. While cosmology leaped to the larger scales, stellar astronomy dove deeper into the fates of individual stars, translating Hertzsprung-Russell diagrams, which plotted stellar luminosity against temperature, into life stories. Low-mass stars like our Sun spending billions of years on the main sequence fusing hydrogen into helium in their cores, then swelling into red giants, shedding outer layers as planetary nebulae, and leaving behind dense white dwarfs, while more massive stars burn through successive fusion stages, helium, carbon, neon, oxygen, silicon, until they build an iron core that cannot yield energy by fusion and collapses, driving a core collapse supernova that either leaves behind a neutron star or a black hole. Neutron stars are among the strangest objects yet discovered, remnants barely 20 kilometers across, packing more mass than the Sun into a sphere the size of a city, composed largely of neutrons jammed so tightly that a teaspoon of their matter would weigh as much as a mountain on Earth, and when they spin rapidly with strong magnetic fields, they emit beams of radiation that sweep across space like lighthouse beams, appearing to distant observers as pulsars whose radio pulses arrive with such regularity that the first ones discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish were briefly nicknamed LGM for Little Green Men, so clock-like were their signals. Black holes, predicted as extreme solutions to Einstein's equations, were long seen as mathematical curiosities until X-ray astronomy and radio observations revealed compelling candidates, where unseen masses in binary systems siphoned matter from companion stars, forming hot accretion disks and jets. These stellar mass black holes were later joined by the recognition that at the centres of most galaxies, including our own, lurked supermassive black holes millions to billions of times the Sun's mass, such as Sagittarius A at the heart of the Milky Way, whose presence was pinned down by tracking the tight, fast orbits of nearby stars whipping around something invisible yet immensely massive. In 2015, another chapter in astronomical history opened when the Laser Interferometer Gravitational Wave Observatory, LIGO, detected tiny ripples in space-time produced by the merger of two black holes about 1.3 billion light-years away, confirming a century-old prediction of general relativity and inaugurating the era of gravitational wave astronomy, where cataclysms once hidden from electromagnetic view, colliding neutron stars, collapsing stellar cores, and perhaps even echoes of the Big Bang itself, could be heard through distortions in the metric of space-time stretching and squeezing kilometre-scale laser arms by distances smaller than a proton's diameter. Astronomy had long since expanded beyond visible light, capturing phenomena in radio, infrared, ultraviolet, X-ray and gamma-ray bands, each revealing different processes. Cold hydrogen clouds glowing in 21-centimetre radio emissions tracing the Milky Way's spiral arms, dusty star-forming regions hidden in optical images but blazing in infrared, active galactic nuclei spewing X-rays and gamma-rays as matter spirals towards supermassive black holes, and gamma-ray bursts flashing as the briefest and brightest explosions in the universe, likely associated with collapsing massive stars or merging neutron stars in distant galaxies. The second half of the 20th century and the beginning of the 21st saw the conquest of near-Earth space, as rockets launched telescopes above the blurring, absorbing atmosphere, giving us instruments like the Hubble Space Telescope, whose 1990 deployment and subsequent repair missions delivered images so sharp and deep that the Hubble Deep Field, a long exposure on an apparently empty patch of sky, revealed thousands of galaxies in an area smaller than a grain of sand held at arm's length, demonstrating viscerally how densely packed the universe is with island universes invisible to the naked eye. Beyond Earth orbit, robotic explorers like the Voyager 1 and 2 spacecraft launched in 1977 conducted the grand tour of the outer planets, Jupiter's turbulent bands and Great Red Spot, Saturn's delicate ring system, a flattened cathedral of ice and dust, Uranus's sideways rotation with its poles tipped toward the Sun, Neptune's supersonic winds and the dark storms of its methane atmosphere, before sailing outward into the heliosheath and interstellar space, carrying with them the golden records etched with sounds and images of Earth. A cultural flourish that transformed a routine mission manifest into a time capsule for any intelligence that might one day snare those tiny emissaries drifting between stars. Closer to home, missions to Mars like Viking, Spirit, Opportunity, Curiosity and Perseverance mapped the red planet's surface in ever greater detail, confirming that liquid water had once flowed there in rivers and lakes, carving valleys and depositing sediments, and orbiters at Jupiter and Saturn such as Galileo Cassini and Juno discovered oceans hidden beneath icy crusts, on moons like Europa and Enceladus, where plumes of water vapour and organic molecules erupt into space, feeding speculation that these subsurface seas, kept liquid by tidal heating and insulated by thick ice, could host microbial life in darkness, making them some of the most tantalizing targets in the search for life beyond Earth. Meanwhile, astronomers on Earth pressed forward with one of the most dramatic revolutions since Copernicus: the discovery of exoplanets, worlds orbiting other stars, which began in earnest in 1995 when Michel Mayor and Didier Queloz announced the detection of a hot Jupiter, 51 Pegasi b, orbiting so close to its star that its year lasted only about 4 Earth days, a planet revealed not by direct sight but by the subtle wobble its gravity induced in the star's motion along our line of sight, detectable as tiny Doppler shifts in the star's spectral lines. The radial velocity method was soon complemented by the transit method, which watches for the minute dip in a star's brightness when a planet passes in front of it, like a tiny eclipse, and space telescopes like Kepler, launched in 2009, stared at tens of thousands of stars continuously, netting thousands of planets of all sizes and periods, from scorched super-Earths, skimming their suns at blistering distances, to temperate Earth-size candidates in habitable zones, where liquid water could exist on the surface, proving that planets are not rare anomalies but common byproducts of star formation, perhaps outnumbering stars in our galaxy. Some of these exoplanets defy imagination. Worlds with years shorter than a single Earth day, tidally locked so that one side bakes in permanent daylight, while the other lies in endless night. Gas giants puffed up by heat until they nearly brush their Roche lobes, shedding atmospheric material into space. Planets with densities suggesting compositions of almost pure water, forming deep global oceans with pressures at the bottom that would crush earthly submarines. And hot Neptunes and super-Earths in configurations that have no analogue in our solar system, forcing planet formation theories to stretch or break. With refined spectroscopic techniques, astronomers have begun to probe the atmospheres of some transiting exoplanets, detecting sodium, water vapour, methane, carbon dioxide, and exotic clouds of silicate aerosols or titanium oxide, and as instruments improve, they aim to sniff out biosignature gases on small rocky planets, combinations like oxygen and methane out of chemical equilibrium, or perhaps more subtle disequilibria, that might hint at biological activity, raising the possibility that sometime in the coming decades, a telescope will quietly register a faint telltale spectral fingerprint from a pale point of light orbiting a distant star, and humans will read in that pattern the first indirect sign that life has taken hold elsewhere. Back on the ground, giant segmented mirror telescopes like Keck in Hawaii, the Very Large Telescope in Chile, and the coming Extremely Large Telescope and 30-meter telescope push angular resolution and light-gathering power to new frontiers, while adaptive optic systems, deforming mirrors hundreds of times per second to cancel the twinkling caused by atmospheric turbulence, sharpen images to near space-based quality, permitting, among other feats, direct imaging of exoplanets as faint specks near glary host stars and detailed tracking of stellar orbits around Sagittarius A. Confirming its mass of about 4 million suns, radio astronomy has also built monuments to human curiosity. The Arecibo dish in Puerto Rico, now collapsed but once famous for radar mapping near-Earth asteroids and broadcasting the Arecibo message toward the globular cluster M13. The Very Large Array in New Mexico, whose movable dishes link together to form a synthetic aperture spanning kilometers, and the Event Horizon Telescope, a global network of millimeter wavelength radio observatories synchronized via atomic clocks to act as an Earth-sized interferometer, which in 2019 released the first direct image of a black hole's shadow in the galaxy M87, a dark, circular silhouette against a glowing ring of infalling gas, providing visual confirmation of an object whose defining feature is that not even light can escape its gravitational grip. Across these centuries, one thread runs straight and taut. Astronomy repeatedly overturns parochial assumptions about our place in the cosmos, each time replacing a comforting centrality with a more humbling yet more majestic vista, from the recognition that Earth orbits the Sun to the realization that the Sun is a typical star in an ordinary spiral arm, that the Milky Way is one galaxy among trillions. that the visible matter we see is a minority component in a universe dominated by unseen dark matter and dark energy, and that our entire observable cosmos may itself be just a bubble in a larger multiverse whose other domains, if they exist, are forever beyond our light cone. And yet, for all this vertigo, the same human impulse that sent Babylonian scribes to rooftops, Greek philosophers to seashores with sticks and shadows, Chinese astrologers to palace towers, Islamic scholars to stone-walled observatories, European monks to monastery cloisters, and modern engineers to mountaintops and control rooms still lives whenever someone steps outside on a clear night, lets their eyes adjust, and feels the weight and wonder of those distant lights, knowing now, in a way none of our ancestors could, that each star is a sun with its own planets, that some of those planets may have their own skies dotted with their own constellations, and that on some of them, perhaps, other beings may be standing at this very moment looking up and asking, as we have always asked, what it all means and how far it all goes, while the universe goes on expanding, cooling, evolving and scattering its secrets across the deep, dark ocean of space for any mind patient enough to fish them from the starlight. If you follow that line of curiosity further, you find that long before any spacecraft skimmed past the outer planets, or any radio dish caught the whisper of a distant quasar, entire civilizations built their cities, their myths, and even their political authority around the choreography of sun, moon, and stars, so that astronomy became not only a path to physical truth, but a scaffold for culture itself, rising from stone and soil toward the sky it tried to understand. On the Yucatan Peninsula, the Maya raised pyramids whose stairways counted the days, like at Chichen Itza, where the Temple of Kukulkan is aligned so precisely with the equinoxes that on those 2 afternoons each year, the setting sun casts a serpent-shaped shadow that seems to slither down the northern staircase, turning stone geometry into a celestial performance that fused religion, rulership, and solar mechanics in a single, astonishing spectacle timed to the Earth's orbit. Maya astronomer priests recorded cycles of Venus with such obsessive care that the Dresden Codex, one of the few surviving pre-Columbian manuscripts, contains tables capable of predicting Venus's appearances and disappearances with an error of only a few hours across centuries, because for them this brilliant morning star and evening star was not just an ornament of the dawn and dusk, but a warlike deity whose rising could sanction battles or sacrifices, binding human bloodshed to the clockwork of planetary motion. Further south, in the high Andes, the Inca wove dark constellations from the coal-black dust lanes of the Milky Way, seeing shapes not only in the bright stars but in the shadows between them. Llamas, foxes, serpents, so that animals critical to their pastoral life were mirrored not as starry dots, but as inky silhouettes in that pale river of light. And near Cusco they built sight lines and pillars that marked solar extremes, effectively creating a city calibrated to solstices and zenith passages, using the sun's noontime height to anchor their agricultural and ritual calendars. On the other side of the world, Aboriginal Australians maintained oral star law for tens of thousands of years, where constellations like the Emu in the sky were mapped, again not by bright stars but by the same Milky Way's dark lanes, and where the rising of certain stars signalled the egg-laying season of specific birds or the appearance of particular foods, intertwining ecological knowledge with celestial patterns in a web so dense that when anthropologists finally wrote some of it down, they realised a sophisticated astronomical tradition had been quietly tracking precession, seasonal shifts and even rare events like eclipses with no need for written math at all. Even in Neolithic Europe long before Babylonia etched clay tablets or grease-polished geometry, rings of stones like Stonehenge rose from the misty plains of Salisbury, their massive sarsens and bluestones arranged to frame the midsummer sunrise and midwinter sunset, while similar, though less famous megalithic structures across Britain and Ireland aligned with lunar standstills and major solar events, suggesting that for those ancient builders, knowing where the sun would be on the horizon on particular days was as essential to their ritual life as tracking the tides of the nearby sea. At Newgrange in Ireland, a passage tomb older than the pyramids, a narrow stone corridor aimed so exactly at the winter solstice sunrise that for a few minutes on those mornings, sunlight pierces deeply into the burial chamber, illuminating its carved spirals and geometric motifs, a cosmic spotlight that may have symbolised the yearly rebirth of the sun, and whose precision testifies that its builders watched the horizon year after year, patiently refining the structure until sky and stone matched with exquisite accuracy. To translate the sky into something portable, scholars in the Islamic Golden Age perfected the astrolabe, a brass analog computer that fit in the hand yet could, when you rotated its star map, its rete, over engraved coordinate circles, tell you the time at night from the altitude of a known star, the direction of Mecca from any latitude, the time of sunrise or sunset, and even solve trigonometric problems, all by sliding metal pointers and reading off angular scales, making it the smartphone of the medieval astronomer, navigator, and theologian alike. European mariners adopted and adapted the astrolabe and later the sextant, marrying angular measurements of the sun at noon or of Polaris at night with increasingly accurate printed tables, and by the 18th century the outstanding challenge in navigation, the determination of longitude, was finally cracked not by a new kind of star but by a new kind of clock, when John Harrison's marine chronometers maintained accurate time at sea, allowing sailors to compare local solar noon with a fixed reference time, and deduce their east-west position from the modest difference in hours, turning the planet into a coordinate grid tied to the heavens. The desire to pin Earth's position relative to the Sun more precisely even led to global observing campaigns during the rare transits of Venus across the solar disk in 1761 and 1769, when astronomers spread out from Siberia to Tahiti, carefully timing how long Venus took to cross the Sun from different latitudes and longitudes, hoping to use parallax geometry to nail down the astronomical unit, the distance between Earth and Sun, more accurately than ever before, though clouds, wars, and logistical chaos conspired to blur their results, reminding everyone that the cosmos might be calculable, but weather and politics were not. Once the astronomical unit was measured well, it became the fundamental rung on what distance scaling astronomers call the cosmic distance ladder, a series of interlocking techniques, parallax, main sequence fitting in clusters, Cepheid variables, type Ia supernovae, that step-by-step expand our reach from nearby stars to remote galaxies, and one of the more subtle rungs involves using the brightness of star clusters, whose ages we infer from their turn-off points in the Hertzsprung-Russell diagram, converting the life cycles of stars into measuring sticks for the size and age of the universe itself. The relationship between the heavens and Earth is not all serene guidance and elegant geometry. Sometimes, as the pocked face of our moon reminds us, cosmic debris slams into planets with catastrophic force, and for most of history, humans had no idea that some of the shooting stars streaking overhead were grain of sand-sized fragments of rock burning up, or that occasionally much larger objects punched through the atmosphere and excavated craters miles wide, like the Barringer crater in Arizona, a 1.2-kilometer wide scar left about 50,000 years ago by a nickel-iron meteorite perhaps 50 meters across. For centuries, many learned Europeans scoffed at reports of stones falling from the sky, dismissing them as superstition, until in 1803, a spectacular meteorite shower near L'Aigle, France, scattered thousands of fragments over the countryside, leading the physicist Jean-Baptiste Biot to investigate and convincingly show that these rocks were indeed extraterrestrial, a conclusion that not only vindicated rural witnesses, but opened a new line of inquiry into the early solar system, as meteorites turned out to be time capsules preserving primitive material from the epoch when planets were first assembling. Perhaps the most famous cosmic collision in Earth's deep history is the Chicxulub impact 66 million years ago, when an object around 10 kilometers in diameter slammed into what is now the Yucatan Peninsula, releasing energy equivalent to billions of nuclear bombs, excavating a crater more than 150 kilometers wide, igniting global wildfires, and throwing so much dust and sulfur into the atmosphere that photosynthesis faltered, and 3/4 of all species, including the non-avian dinosaurs, vanished, an event inferred from a thin global layer rich in the rare element iridium and shocked quartz, and from the buried shape of the crater itself, which geophysicists mapped centuries after its fiery birth. Near misses and smaller events remind us that such impacts are not confined to the imagination or the deep past. In 1908, an airburst over Tunguska in Siberia flattened 2,000 square kilometers of forest, likely caused by an object perhaps 50-60 meters across exploding in the atmosphere, and in 2013 the Chelyabinsk meteor, around 20 meters in size, detonated over Russia with a shock wave that shattered thousands of windows and injured over 1,000 people, prompting renewed attention to near-Earth object surveys, which now use wide-field telescopes and automated software to map the orbits of hundreds of thousands of asteroids and comets that cross our planet's path. The broader asteroid belt between Mars and Jupiter, discovered piecemeal in the 19th century with Ceres, Pallas, Juno and Vesta as some of the first recognised members, once tempted astronomers with the notion of a shattered planet. But dynamical studies increasingly suggest that Jupiter's gravity prevented a full-size planet from coalescing there, leaving behind a population of rubble and protoplanetary leftovers whose compositions, carbonaceous, stony, metallic, tell stories about temperature gradients and material sorting in the early solar nebula, and which space missions like Dawn have visited, orbiting Vesta and Ceres to reveal differentiated interiors and, in Ceres' case, mysterious bright salt deposits hinting at past brines. Beyond Neptune, the Kuiper Belt, and farther still, the hypothesized Oort cloud harbour icy bodies that represent another kind of cosmic archive, preserving ices rich in volatile compounds like methane, ammonia, and complex organic molecules. And when some of these travel inward as comets, they not only paint graceful tails across our sky, but also deliver chemical samples to our laboratories, either through collected dust or meteorites. Samples that have yielded amino acids, nucleobases, and other prebiotic ingredients, fueling the idea that some of life's essential components may have been delivered to early Earth by a long reign of cosmic messengers. In dense molecular clouds between the stars, radio and millimeter wave telescopes like ALMA and single-dish instruments at places like Green Bank have detected an astonishing variety of molecules, over 200 and counting, including simple alcohols, sugars like glycolaldehyde, precursors to amino acids, and even chiral molecules with handedness similar to those in terrestrial biology, suggesting that the galaxy is chemically fertile, with complex organics forming on dust-grained surfaces, being irradiated by ultraviolet light and then stirred into protoplanetary disks where young worlds are condensing. Astrochemists have even identified fullerenes, carbon molecules shaped like soccer balls, and large polycyclic aromatic hydrocarbons in interstellar space, hinting that carbon's versatility is exploited far beyond our biosphere, and when meteorites like the Murchison fall to Earth and are examined, their isotopic ratios and molecular assemblages often bear the signature of formation in cold, irradiated environments light years away, so that every such rock is both a fragment of our solar system and a relic of interstellar chemistry that predates the Sun. Back at the larger scales, as technology opened the radio window in the mid-20th century, astronomers stumbled on entirely new kinds of objects that had no analogue in classical optical catalogues, starting with quasars, quasi-stellar radio sources, which appeared as star-like points in visible light yet emitted prodigious amounts of energy across the electromagnetic spectrum, and whose spectra, when Martin Schmidt correctly interpreted their redshift in 1963, placed them billions of light-years away, meaning they outshone entire galaxies even as they fit within a region only light days or light weeks across. Those infernal powerhouses were soon understood as active galactic nuclei powered by accretion onto supermassive black holes, where matter swirling inward in a disk heats to tremendous temperatures and magnetic fields, funnel some of the inflowing mass into twin relativistic jets that can stretch hundreds of thousands of light-years, punching out of the host galaxy into intergalactic space, their synchrotron glow visible across cosmic time, and offering one of the most dramatic demonstrations that gravity, when assisted by rotation and magnetism, can turn falling gas into beams of radiation bright enough to rival the glow of 1 trillion suns. Another phenomenon predicted by general relativity and later pressed into service as a cosmic tool is gravitational lensing, where mass bends space-time enough that light from a background object is deflected, much as a glass lens refracts beams, and when background galaxies are perfectly or nearly aligned behind massive foreground clusters, their images appear as arcs, rings, or multiple distorted copies on the sky, like the famous Einstein cross, where a single quasar appears as 4 points around a closer galaxy, each image following a slightly different path through the curved space. Far from being mere curiosities, these gravitational lenses allow astronomers to map the distribution of both visible and dark matter in clusters, because the degree and pattern of distortion encode the underlying gravitational potential, and by modelling the lensing, researchers have demonstrated that clusters contain several times more mass than their luminous galaxies and hot gas can account for, offering some of the strongest evidence for dark matter's existence, and showing how cosmic structure binds together into filaments and nodes in the vast web-like pattern revealed by redshift surveys like the Sloan Digital Sky Survey. Those surveys, which have measured positions and redshifts for millions of galaxies, sketch a three-dimensional map of the universe out to billions of light-years, unveiling features like the Great Wall, a colossal filament of galaxies stretching hundreds of millions of light-years, and huge voids hundreds of millions of light-years across, where comparatively few galaxies reside. So that if you could see the cosmos not as points of individual stars, but as a fog of dark matter and galaxies, you would witness a foamy structure with luminous threads and empty bubbles, shaped by primordial quantum fluctuations amplified by gravity. In parallel, precision cosmology has used subtle ripples in the distribution of galaxies, known as baryon acoustic oscillations, the frozen imprint of pressure waves in the hot plasma of the early universe, to cross-check the expansion history inferred from supernova and the cosmic microwave background, providing independent evidence that the universe's expansion is accelerating and that space on its largest scales is remarkably flat, an outcome that inflationary models of the very early universe elegantly predict, but whose underlying mechanism, perhaps driven by a scalar field rolling across a potential energy landscape, remains a tantalizing mystery. To peer deeper into cosmic history, astronomers chase the epoch of Rayonization, when the first generations of stars and galaxies ignited after the cosmic dark ages and their ultraviolet light rayonized neutral hydrogen gas, turning the universe from a foggy, opaque medium into a transparent one. This transition left characteristic signatures in the absorption spectra of distant quasars, like the Gunn-Peterson Trough, and new instruments like the James Webb Space Telescope are now detecting surprisingly bright chemically evolved galaxies at redshifts greater than 10, corresponding to a time less than 500 million years after the Big Bang, challenging models of how quickly structure could assemble. JWST's infrared eyes, cooled to just a few degrees above absolute zero and stationed at the Sun-Earth L2 Lagrange point, let it see through dust into stellar nurseries and examine redshifted light from early galaxies that is invisible to Hubble, and already it has revealed clumpy disks of dust and gas where planets are coalescing around young stars, with gaps possibly carved by nascent worlds, adding protoplanetary disks to the historical record of astronomy subject matter, which began with points of light and now stretches to include embryonic solar systems in various stages of formation. As our instruments grew more sensitive, we discovered that the Sun itself participates in a cosmic particle game hidden from ordinary sight. It produces an immense flux of neutrinos, ghostly, nearly massless particles born in nuclear reactions in its core that stream through space and through our bodies by the trillions every second, barely interacting with normal matter, and early neutrino detectors like the Homestake experiment in South Dakota, a tank of cleaning fluid buried deep underground, found only about 1/3 of the expected solar neutrinos, a discrepancy that sparked the solar neutrino problem, and raised the unsettling possibility that we misunderstood either the Sun's interior or the particle zoo. The resolution came from particle physics. Neutrinos have mass and can oscillate between different flavors, electron, muon, tau, as they travel, so detectors sensitive to only one flavor naturally see a deficit. And when observatories like Super Kamiokande in Japan and the Sudbury Neutrino Observatory in Canada confirmed these oscillations, they both vindicated the solar models and established that neutrinos are not exactly massless, a finding that required an extension of the standard model of particle physics and showed once more how astronomy and particle physics weave into a single fabric. Neutrinos also offer a new window on violent events. When the nearby supernova SN 1987A exploded in the Large Magellanic Cloud, underground detectors in Japan and the United States registered a burst of neutrinos hours before the visible light peaked, heralding the core collapse and demonstrating that neutrinos carry away most of the gravitational binding energy when a massive star's core implodes to a neutron star, so that in a future galactic supernova, a flood of neutrinos will reach our detectors almost at once, offering an early alarm and a detailed probe of the explosion's otherwise hidden heart. High-energy cosmic rays, discovered when balloon-borne detectors showed that radiation increased with altitude rather than being solely of terrestrial origin, turned out to be charged particles, mostly protons and heavier nuclei, accelerated to near-light speeds by shockwaves in supernova remnants, jets from active galaxies, and perhaps as yet unknown engines, and these cosmic bullets can carry energy so extreme that a single particle can rival the kinetic energy of a thrown baseball, slamming into Earth's atmosphere and producing showers of secondary particles that spread across many square kilometers and are hunted by vast observatories like the Pierre Auger Observatory in Argentina. Astronomy has even become a tool for testing the constancy of fundamental constants, because spectra from distant quasars, whose light has traversed billions of years and expanded with the universe along the way, can be scrutinized for subtle shifts that might indicate changes in quantities like the fine structure constant, which sets the strength of electromagnetic interactions. And although most measurements so far support stability, the mere fact that we can contemplate checking whether the laws of physics have drifted over cosmic time speaks to how precisely we can now compare atoms in cryogenic labs with gas clouds halfway to the edge of the observable universe. Amid this panorama of data and theory, the search for life elsewhere has spawned its own branch of observational effort, SETI, the search for extraterrestrial intelligence, which began in earnest in 1960 when Frank Drake pointed a radio telescope at two nearby sun-like stars in Project Ozma, listening for artificial signals, and later codified his reasoning in the Drake equation, which multiplies factors like the rate of star formation, the fraction of stars with planets, the fraction of planets where life arises, where intelligence evolves, where technology emerges, and the average lifetime of communicative civilizations, not to produce a precise answer, but to frame our ignorance in structured form. As radio telescopes grew more powerful and computational capacity exploded, projects like Serendip and Breakthrough Listen undertook large-scale, systematic scans of the sky across multiple frequencies, feeding petabytes of data into algorithms, including, more recently, machine learning models, searching for narrowband beacons, pulsed signals, or techno-signatures like unusual patterns that natural astrophysical processes do not readily mimic. And although no confirmed signal has yet survived scrutiny, the effort itself represents a shift from idle speculation about aliens to a quantitative, testable survey of a small fraction of the cosmic haystack, where other technologies, if they exist, might reveal themselves. Closer to Earth, the concept of a habitable zone, the orbital band around a star where a planet could sustain liquid water on its surface, given a suitable atmosphere, has become central to exoplanet studies. But astronomers have learned that this zone is not static. It moves outward as stars brighten over time, and its actual habitability depends on factors like greenhouse gas composition, planetary mass, magnetic field strength, rotation rate, and even continental configuration, so that two planets at the same distance from similar stars can have radically different fates, as the comparison between Earth and Venus so eloquently shows. Venus, once imagined as a twin of Earth shrouded in tropical clouds, turned out, when radar and spacecraft peeled back its veil, to be a hellscape of crushing pressures and surface temperatures hot enough to melt lead, a runaway greenhouse world where a thick carbon dioxide atmosphere and clouds of sulfuric acid trap heat with brutal efficiency, thereby serving as a cautionary counterexample to Earth's delicate balance and offering planetary scientists a laboratory for studying climate extremes, atmospheric superrotation, and volcanic resurfacing on a planet that may once have had shallow oceans before losing them to the sun's relentless ultraviolet glare. Mars, by contrast, bears geomorphological scars of past rivers, deltas, and perhaps even lakes or shallow seas, yet now shivers under a thin, mostly carbon dioxide atmosphere with surface pressures less than 1% of Earth's, and evidence from orbiters and rovers suggests that its magnetosphere faded early, allowing the solar wind to strip much of its atmosphere away, a process confirmed by NASA's MAVEN mission, which measured ongoing atmospheric escape, showing how a planet's magnetic field, or lack of one, can determine whether it remains a water-bearing bastion or dries into a frozen desert. Within our own star's life, Earth's climate has danced to a slower astronomical rhythm as well, governed not only by greenhouse gases and tectonics, but by subtle variations in orbital parameters known as Milankovitch cycles. The eccentricity of Earth's orbit, the tilt of its axis, obliquity, and the precession of that axis all change with characteristic periods of tens to hundreds of thousands of years, modulating the distribution of sunlight across latitudes and seasons, and paleoclimate records from ocean sediments and ice cores show clear signatures of these cycles pacing the advance and retreat of Pleistocene ice sheets. When Serbian mathematician Milutin Milankovic refined the calculations of how these orbital changes alter insolation at high latitudes, he connected celestial mechanics directly to glacial geology, demonstrating that Earth's deep time climate is in part an astronomical phenomenon, and that our planet's path through space, once thought to be a static ellipse, actually shuffles subtly under the gravitational influences of other planets, mixing a kind of cosmic music into the long-term behaviour of ice, oceans and living ecosystems. The Sun itself is not perfectly constant either. It exhibits an approximately 11-year cycle of magnetic activity marked by the waxing and waning of sunspots, flares and coronal mass ejections, and historical records of aurorae, combined with tree ring data containing spikes of radiocarbon from solar Proudhon events, let us reconstruct centuries of solar behaviour, including the Maunder minimum, a deep 70-year lull in sunspots from about 1645 to 1715, when winters in parts of Europe were harsh enough to freeze the Thames, raising intriguing questions about how stellar magnetic cycles can subtly influence planetary climates without being the primary drivers of major modern warming trends. Astronomy's reach into human affairs even extends to our clocks and coordinate systems in the present moment. The definition of the second is tied to oscillations in cesium atoms, but leap seconds are occasionally inserted to keep coordinated universal time aligned with Earth's slightly irregular rotation, which itself is influenced by tidal friction from the Moon, core mantle interactions, and even large-scale weather and glacial rebound, so that our civil timekeeping dances subtly around an astrophysical reality. That a day is not a perfectly fixed quantity, but a compromise between the spinning of a lumpy, slowly breaking planet and the relentless precision of atomic transitions. Space-based geodesy and missions like Gaia, which is mapping the positions, distances and proper motions of more than 1 billion stars with micro-arcsecond precision, have transformed our understanding of the Milky Way from a conceptual spiral sketch into a dynamic structure whose stellar streams betray past mergers with dwarf galaxies, whose warp and flares at the edges suggest ongoing gravitational torques, and whose central bar and spiral arms can be traced not just in gas and young stars but in the kinematics of old populations, turning our galaxy from a static backdrop into a roiling cannibalistic organism still digesting the smaller systems it has devoured. Gaia's data have revealed that the Milky Way experienced a major collision about 10 billion years ago with a dwarf system nicknamed Gaia Enceladus, or the Sausage Galaxy, an event that puffed up our stellar halo and left behind distinct kinematic signatures, while streams like the Sagittarius and GD1 arcs trace the orbits of smaller galaxies and clusters being tidally shredded, offering living examples of hierarchical structure formation, where large galaxies grow by accreting smaller neighbours and mixing their stars like dye poured into a swirling flow. On a more speculative frontier, some astronomers and SETI researchers have proposed that advanced civilizations might betray their presence not through deliberate beacons but through large-scale engineering projects. For example, hypothetical Dyson spheres or swarms harvesting much of a star's energy output and re-radiating it in infrared. So surveys like the Glimpsing Heat from Alien Technologies GHAT project have combed all sky infrared data for galaxies with anomalously high mid-infrared emission relative to their starlight, essentially searching for cosmic-scale waste heat. And while nothing conclusive has emerged, the methodology represents a radical shift, using astronomy to look not only for what nature produces but for what may be the byproducts of technology writ large. Magnetars, a subclass of neutron stars with magnetic fields 1,000 trillion times stronger than Earth's, remind us that even within known categories there are extremes almost beyond imagination. Their crusts can crack in starquakes that unleash giant flares of gamma rays detectable across the galaxy, and some enigmatic fast radio bursts, millisecond scale, extremely luminous radio flashes from distant galaxies are now thought to arise, in at least some cases, from magnetars flaring or colliding with their environments, making these compact objects central suspects in a mystery that has captivated high-energy astrophysics for over a decade. As astronomers continue to map the sky in time as well as in space, with projects like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, which will repeatedly image the entire accessible sky every few nights for 10 years, they're entering an era of time-domain astronomy, where the focus shifts from static catalogues of objects to movies of a dynamic universe, in which supernovae ignite and fade, variable stars pulse, black hole binaries flicker, and perhaps entirely new classes of transient phenomena, unknown today, will appear in the flood of data, waiting for some keen eye or clever algorithm to recognize their alien signatures in the ceaseless swell of starlight and shadow.